Welcome to this video on how to solve PDEs in Mathcad Prime. The heat equation models the flow of heat in a rod that is insulated everywhere except at the two ends. Solutions to this equation are functions of two variables. One spatial variable, the position along the rod, and time. Suppose that the rod has a length L in meters, here set to 1 meter, and we impose an x-axis along the rod as illustrated. Here to the right, we have the temperature distribution function g of x. It's defined to be 100 degrees at the left end of the rod. The rod has a temperature of 25 degrees and 0 degrees at the right end of the rod. This function g of x is called the initial condition. The boundary conditions are the constant temperatures at the ends, 100 at the left end and 0 at the right end. To solve the heat equation under these conditions, we'll use the function numol, which has the syntax. To use this function, we must provide 9 parameters. The first 6 of them are quite simple. The first x points from 0 to L entered in a matrix. 0, L. Then the number of x points, let's say 50. T endpoints, again a matrix, and let's enter from 0 to say 4, again with 50 T points. All in all, this gives us an XT grid of 2,500 points to approximate the solutions. Now to the number of PDEs, number of differential equations. Here we have only one. Number of PDEs, this is partial algebraic equations, none. Now the PDE function. Here we have to rewrite the right-hand side in terms of x, t, u, x, the first derivative of u with respect to x, and u double x, the second derivative of u with respect to x. That is a function right-hand side RHS of x, t, u, x, and this x must be written as literal subscript, comma, and u double x, colon equals, and we can write this equation as a times u double x. So the function name RHS is our next parameter, comma. The init function, the initial condition, just enter g. Finally, for the BC function, that is the boundary condition, we can write it as BC function of x colon equal a 1 by 3 matrix, where we have 100, 0, and a D, where D stands for the Dirichlet condition, meaning that we are using the temperature values at the endpoints and not the gradients, in which case we must write an N, short for Neumann condition. So here, just enter the function name. Finally, let's assign the output of the numol function to a variable S. The solution is a 50 by 50 matrix, where the columns are the temperature distribution in the rod at a given time. The rows are temperature versus time at a given position along the rod. Let's draw some graphs. In the first plot, we have graphed some of the columns in the matrix S. This shows us the temperature distribution at a given time. In the next plot, we have graphed some of the rows in the matrix S. The first graph, the blue one, shows that in position about 2 centimeters from the left end, the temperature will start at 25 degrees, then increase rapidly, and then slowly reach the final temperature of about 96 degrees. We can also make a 3D plot where the grid more or less shows the two plots we already have made. We can follow the grid from the initial distribution, see it here, to the final linear distribution. And if we follow the curves here starting at 25 degrees, we can follow them here. This corresponds to the second plot. Finally, we can draw a contour plot. Along the axis, we have the matrix indices. The x-axis is the position and the y-axis the time. The different colors shows the temperature at a given position and time. Now let's move on to our next example. In this example, we model the vibrations of the stretched string of length L. Think of a guitar string. We will not go into details with this example, just show how to use the numol function to solve this equation. The graph shows the initial position of the string. The string is fixed at both ends. This is the boundary conditions, and the graph itself, or the function, is the initial condition. To use the numol function, the left-hand side of the PDE must be the first derivative with respect to t, so we have to rewrite the PDE. We define a new function called v to be the partial derivative of w with respect to t. Having introduced v, we are now able to rewrite the wave equation as this equation. Now, the wave equation is written as a system of two PDEs, and both PDEs have the first derivative with respect to t on the left-hand side. So the PDE function is RHX, a function of xt, u, ux, and u double x. Let's take a look at the system. The first equation has a v on the right. This is u1. The second equation is a times the double derivative of u, and the double derivative of u with respect to x is a vector, and we'll take the first component of that vector. Now to the init function. The init function is the initial condition for w and for v. At the beginning, we had no initial condition for v. It wasn't even introduced, so we have to add something as initial condition for v. I've set it to 0. So this is our init function, g of x, and 0 for the initial condition of v. The BC function, g of 0, g of L, this is 0 as the string is fixed. The Dirichlet condition for the v function We have no boundary conditions. So NA here means not available, and the D, as before, refers to the Dirichlet condition. Everything is ready for the numol function. Note that we here have two PDEs. We have assigned the output of the numol function to S, and let's take a look at the columns in S. There are hundreds, and there are 100 rows. This may be a bit surprising, as we have only 50 T-points. So there should only be 50 columns. But here we have a system of two PDEs. So the first 50 columns are for W, the last 50 columns are for V. So we have to be careful when drawing graphs. Let's take a look at some of them. In the first graph, we have the solutions for W, displacement of the string at a given time. In our second graph, we have the solutions for V. This is the last 50 columns of the matrix S. In this graph, we have the rows of the matrix. This is time versus displacement at a given position along the string. And finally, we have a 3D plot. This is the initial position of the string. Here we have the final position of the string. That's all for now. Thanks for watching.